Hi, I'm Rick with PLP Battery Supply, and today what we're going to talk about is how battery chargers work and what is the magic on the inside of that box that makes power go in through the AC cord and then battery charging happens on the other side. So what we're going to do is we're going to use a little visual aid here that we call a Franken-Charger, because this thing is assembled from a variety of parts, but it's just meant to show you how everything functions and why it does what it does and what the issues are that you're liable to encounter whenever you're working on a battery charger. So what we're going to do is we're going to start out with sort of what the guts of this thing are. This is essentially what you would find in a sort of entry-level wheel charger, maybe something with a 40 amp charge, 200 amp boost, something along that line. This is actually a transformer out of a Schumacher 4022, and then we've got just a variety of some generic parts thrown in here to make this thing work. So, and just by the way, notification right up front, this is not UL approved, it's not OSHA approved. The major hazard with this is actually splinters. So what happens on a battery charger is AC power goes in through the cord, and it goes, in this case, part of it goes into the timer. We do have the ground, that in this case is grounded to the transformer frame, and then you've got the neutral wire that goes over to the switch. So the timer does nothing more than interrupt the AC input coming into the charger right at the beginning. The AC then continues on to the switch, where the switch is going to separate, I shouldn't say separate, it's going to send that AC power to whichever one of the windings in the transformer. In this case, this transformer has 4 windings, so it's got 4 power levels, and the switch sends it to either 1, 2, 3, or 4, whichever one of those windings that we're going to be using to charge our battery. So that's what we call the AC side, or the primary side of the charger. All of everything that we're talking about so far is AC house current. Once it comes out of the transformer, because that's what happens next, is the voltage flows through these wires into the transformer. Transformer does its magic, which is essentially reducing voltage and increasing amperage capacity. And then the wires that come out of the transformer are called the AC secondaries. And what you'll notice is that we go from these little bitty AC wires to these much larger wires here that are capable of handling that increased DC current. So we've got one side of the secondary that comes out and goes to the rectifier. So these are the rectifier inputs. At this point, this is still AC current, but it's lower voltage. It's getting close to battery voltage at this point, but it's still AC. And the transformer also has a neutral output that just basically goes directly to the negative battery cable. So we got some fantastic artwork here. Did you know that this is the negative side? And if we trace it all the way out, that goes to this negative clamp that we've got hooked up to our test battery over here. So the other piece of magic that happens in a charger, aside from the transformer changing the voltage, is this AC now that's coming out of the transformer needs to be converted to DC, because our battery cannot absorb AC voltage. It can only absorb DC. So the way that we make AC into DC is through a rectifier. And a rectifier, basically, if you were to look at this on an oscilloscope and you see the waves, the rectifier basically chops half that off. So then it looks like DC current. So the AC normally that would alternate back through that current, or through that wire back into the AC current into the house, that can't flow back. It can only flow one way, so it's DC for the battery. So when we come out of, once we've converted this to DC, then what we're going to do, and that's this right here. So this whole plate, it goes AC here, There's a bunch of diodes down here that make sure that it can't be AC anymore. It's going to go to DC. So this DC plate is now, I'm sorry, the rectifier plate is now DC. And we're going to pick up our battery voltage to charge our battery off of this plate. And we're going to do that, in this case, with Franken-Charger, off of this little strap right here. We've got it bolted right here. Actually, I'll turn this for you real quickly so that you can see that. This is our output from the rectifier plate, and it's coming up to this strap. And then off of that strap, first we're going to protect our circuit with some circuit breakers. That's what you're seeing right here. This is a pair of 50 amp breakers. And then off of the breakers, on the other side, where we have this strap, we're connecting the meter so that we can monitor how much amperage is coming out. So this is an amp meter. And then on the other side of the amp meter is the DC output to the positive cable. So the current is actually flowing from this plate through these breakers, through the meter, because this meter has an internal bus bar. That current flows through the meter and then out the cable, out to our positive cable, to the positive clamp, and to the battery. So that's the entire journey of our power from the AC cord through the transformer, through the timer and the switch, into the transformer, out of the transformer to lower voltage, through the magic of the rectifier to turn it from AC into DC, and then through some circuit protection, through the meter so we can see what we're doing, and then out, connect to the battery. That's basically all the guts that are in a typical battery charger that you would use like to charge a car. The only major component that you're likely to encounter inside a charger that we don't have on Franken-Charger here is a cooling fan. We just didn't want to put one on here because it's noisy and it's unnecessary in this case. This is for demonstration only. So what we're going to do now is we're going to fire this thing up, and we're going to show you how all this stuff works, and we're going to show you some readings so that you'll know where you can test and what you're liable to see. And the first thing we're going to do is pull a multimeter in over here, turn it on. And we're going to turn our charger on. We don't have any scales or any dials here for you to see. I mean, we've got the knobs, but that turns on. This is the off position over here. Dang. So this is turning the charger on. And so now it's got AC into this, into the switch and into the transformer. We're not showing anything here because the switch still is in the off position. So as soon as we turn the switch to on, and honestly the first position should be a 6 volt, so we shouldn't see anything on this one. But right now this battery is sitting at 12.77 volts. So if we go to our first position, we might be getting a little bit. Let's see what it says. Oops. Yeah, it bumped it up to 12.94. So just barely nudged the needle, but we can do better. So this is our second. This is probably around a 10 amp setting, but because this battery is really very full, it's only showing about 4 amps, which is pretty typical. I'm trying to get these wires kind of straightened out here. There we go. So at this point, we're charging 1388, 1389, and about 2 to 4 amps, something like that, in the charger through the meter. We can keep going higher. Now, I'm going to tell you this: if you're charging a battery and you're getting that kind of voltage under charge, that's probably all the higher you need to go, especially if you're going to leave it on there for more than just a few minutes. If you're going to leave it on for, this is probably a 2-hour duration timer. If you're going to leave it on there for 2 hours, I probably wouldn't turn it up any more than that, because you're going to go well above 14 volts on the next setting. It's a pretty small battery, so it's liable to really spike the voltage. Yeah, see, we're at 16 volts on that setting. So it's putting out, at this point, we're at 10 amps, really, that's a dangerous setting. We can, it's fine for demonstration, but you wouldn't want to leave that on there for any length of time at all. So we'll back it off to our original setting here. And so this is showing you just kind of how the voltage responds to the rate setting. And there's actually one more setting beyond that for boost. That can be pretty dangerous. That's the one thing that I think people tend to abuse and overuse. They'll hook it up to a dead battery, crank it to boost, and try and start the car. These things are capable of enough output that they will damage the rectifier. The rectifiers are typically designed to be sort of the weak link in the system, and it's generally it's the most commonly replaced item in a charger because they are sort of a weak link. The breakers will protect against a massive shock or a massive like reverse connection or something like that, but you can overcome the breakers by overpowering the rectifier and blow components out of the rectifier and damage it. So what's happening on the AC side of this while we got this thing turned on? What are we going to be looking for if we're trying to diagnose something? Well, if we go over here to the AC side of the meter, and let's just take a look and see what we've got. So if I test right here, and then just come over here to ground, that's showing me that our AC input into this charger is 121 volts. That's pretty typical for line voltage. All of these are going to remain the same voltage as they come into the transformer. So it's just diverting from one to the next, to the next, to the next circuit in the transformer. The next voltage that we're going to see and see any change in is this secondary AC voltage as it goes into the rectifier. So if we look at, and the way to test for that is to go probe at the transformer negative output and then test one of your positive outputs where it goes into the rectifier. And this is, again, pretty typical. We've got a reading here of 11.2 volts. So now we're down to about that battery voltage we were talking about before. So it's going in there at 11.2 volts, and that is fairly common. Now if we bump it up, we're going to see that voltage spike. Now it's up at 13.6, and that's yielding that 16 volt at the battery DC that we were talking about earlier. So what you're going to see is the AC secondary is going to jump at each one of these rates. It's going to come up, commensurate with the setting and what you're expecting everything to do. And if you're getting good secondary voltage, if you're seeing that 11, 12 volts, if you're seeing that 13, 14 volts, but then you come down here and you're either checking at the battery or you're checking at the charger itself. We'll go back to DC voltage. See, we're getting that battery voltage right here again, that 14 volts. But let's do something. Do a little test here. We don't have to have this thing hooked up to a battery to test the charger. We got some functions that we need it hooked up to a battery for, but just the basic function of, is this thing working? Is the transformer working? And is the rectifier working? We can do that without having these things hooked up to a battery. So we'll turn it on again, go just to our lowest setting, and if we again test the AC side to see if the transformer is working, we can probe there, probe here, and it's going to show us, well, that's that little 6 volt setting, so it's not going to show us much. Actually, it's not going to show us anything because I'm looking at the DC. There we go. See, it's showing us 10 volts at that first setting. If we push it up, and again, this is open circuit, so the battery is not affecting it at all. And there we're at 11. Here we are at 14. And on this highest boost setting, it's showing 15, almost 16. So those are not uncommon. Those are pretty typical voltages to test one of these things before you ever hook a battery up to it. That tells us that this thing, the transformer, is good and it's working. So at each one of these settings, we've got good voltage on the AC side on the secondary. That's the first thing that you want to know about your battery charger, is whether the transformer is working. So once we know that's working, then we have a fault, then we know that whatever the problem is, it is from this point outward. So it's going to be from the rectifier out. The rectifier, the breakers, the meter, a connection, a clamp. It's somewhere out there because this part is all working. And if we do a little bit, another test to check that stuff, we can do that even. Again, we're going to leave it turned on. We're going to turn on to our first setting on the transformer, and then we're just going to check here. So now we're just checking the DC outputs. Again, this is without the battery hooked up. We got our battery clamp disconnected. So what do we got? 9.8. Next setting, we're up at about 11. The next one, we're at 13. And the next one, we should have that 15 volt. Yeah, here we are, 15.3. So with that test, what it's going to tell us is that all the components, from the rectifier to the breakers to the meter, everything that has to do with the DC output, that's all working. If one of those voltages failed us, and actually at this point, if any of them, there's not going to be a situation where we're going to have one failure. They're going to all be low, because from this point on, they're all using the same, whatever the voltage is coming into the rectifier, it'll be reflected in what's going out. So a normal rectifier failure, the way that would diagnose here is you'd have all those good AC voltages going in, that test that I just performed would yield nothing, because nothing's getting out of the rectifier. So that's just a quick overview on how a battery charger works and how all these things are integrated and how they work together. We're going to do one more thing, and we're just going to quickly hook this back up, and we're going to demonstrate what it looks like on the meter and how the charger reacts when we put a load on it. And what we're going to do is we're going to simulate starting a vehicle. So we're going to pretend like what we're going to do is I'm going to hook a load tester up to it. I'm going to place about 125 amp load on this battery while we have it in boost mode, and we can see how the battery charger responds to that. So we'll hook this little guy up here, and this is a fairly lightweight tester. I just want to point that out. This is not like a heavy carbon pile or anything like that. This is what we call a toaster tester, because all it's got is a little wire, very much like a toaster element. It's got a wire resistor in there to place some load on the battery. So let's get all set up here. We've got the charger turned on, timer's running. We've got AC coming in. We're going to go ahead and put it on. Let's see where we're at. That's our second setting. We're sitting there charging at 13.8. We're going to pretend like we need to go to boost, and you can see that meter jumping up as we turn it. Okay, now it's at its maximum capacity. Watch what happens when I place a load on the battery. That's the charger responding to the load on the battery. It's pegging that meter, and that is not at all uncommon. That's the way that it normally works. If you go to boost start your car and you've got everything hooked up, hit the key, and the meter doesn't react like that, you got a problem with the charger, probably the rectifier. And the other thing I'll say is the absolute most common problem that we have with battery chargers is the rectifier being blown out because folks hook their battery charger up to the battery in their car, and they go to crank it, and they just crank it and crank it and crank it and crank it. If it's not starting, they just keep on cranking it until it starts or until the charger fails. Because you know how we are. If you read the fine print on any of these chargers, it will tell you the duty cycle for the boost is probably, it varies a little bit among manufacturers and among chargers, but it's very typical in the fine print for it to say that it is a 5 or 10 second on cycle. In other words, you can crank for 5 or 10 seconds, and then they want something like a 5 or a 10 minute off cycle. So they want it to rest for 5 or 10 minutes before you crank it again for 5 or 10 seconds. Human beings are human beings, and it doesn't work that way. So folks tend to just crank them until, you know, somebody lets the smoke out of the charger, because that's what happens. Something will let go in here. These are actually designed to fail. They've got this particular type of rectifier has a fusible link connection between the AC side and the diode, and it'll just simply blow. It'll overheat and it'll melt. So it protects sort of everything, but then you have to replace this when it does that. But that's generally what happens, is the charger's used to boost something, boost a vehicle, and it's overused until the charger fails. Good news is they can be rebuilt. You can replace all these components can be easily replaced, but it's just a question of trying to avoid that in the first place. So if you're using a charger to boost something, try not to overdo it. That is pretty much it. Just a quick overview again. AC power comes in, goes through the timer that turns it on. Ding, now we're gonna turn it off. The timer controls the power. It goes to the switch. The switch sends it to whichever one of the discrete windings in the transformer that we want to use for our power setting. The transformer sends that AC power out at a lower voltage to the rectifier, so now it's down around battery voltage. The rectifier changes it into DC so the battery can absorb it, and that's how it works. It is just simply AC coming in, voltage gets lowered, voltage gets changed to DC, goes through some protection, goes through a meter to show you what it's doing, then it's out to the battery. If you guys have any questions, you can always contact us at plpbattery.com, or you can call us at the shop at 800-642-3451. Thanks a lot.